This is P10T5. I'm Jim2303708. Our vision for the abstract engine is for it to be extensible, scalable, and modular to allow for changes and reusability. The key features implemented in this abstract engine is realistic physics simulation, as well as keyboard and mouse interaction with the objects. Here is the demo. When you first launch the game, you'll be greeted with a menu screen. Pressing enter would allow you to start the game. To take note, the water droplets, when it touches either the floor or the bucket, would appear back to the top. When it touches the bucket, it would also play a sound. The triangle moves left and right in a static fashion, but when you click on it, you're able to manipulate its position. Clicking anywhere else would not manipulate the triangle. Right-clicking, however, will teleport the bucket to wherever your cursor is, no matter what. You're also able to manipulate it with the AWS key. The circle can be manipulated with the arrow key and space. Arrow key manipulates its direction, and space manipulates a single time jump action, where in order to go up, you have to press it multiple times. It changes color when you touch the bucket, turning red, and changes to green when you touch the floor. When you press escape, it brings out the pause menu. Note that it renders the game scene as well as rendering the text, but the logic does not move. Pressing M brings you back to the menu screen, and pressing Q quits the game. For a high-level architecture, we went with a separation of concern approach, where they are grouped based on what they are supposed to do. Feel free to pause this to have a quick read. Back to our demo, what if this time we want the bucket to act just like the triangle, where it will only be manipulated when you click on it and move it around, and when you click anywhere else it wouldn't affect it. So we just need to uncomment this. And what about the triangle? Let's say what if we don't want it to be moving automatically anymore. Now we want it to move just like the bucket, where we can manipulate it by WASD. And how about the circle? Let's say what if we want it to act just like the water droplets, where it will only teleport when you either touch the floor or the bucket. And lastly, what about the water droplets? What if we don't want it to do anything at all? Don't want it to respond to collision at all? Just need to comment this. So then now when we run it, you're able to see that it acts differently now. Where the circle would teleport when you either touch the bucket or the floor. Next, how about our triangle? We set it so that it follows along the same movement as the bucket. So then the movement type of the bucket and triangle is now the same. And for the bucket, it now follows the same response where clicking anywhere else doesn't move it, but clicking on it moves it and the triangle. So this is one of the advantages of the component-based approach.
Hi everyone, I'm Fitris and today I'll be walking you through our team's engine scene architecture. In the middle here, you will see our file architect for all our scenes. So we have demo scene, scene control, menu scene, pause scene, scene itself, and the scene manager. So we have a total of 6 scene files. To manage the flow of the game, we implemented a stack-based state machine inside the scene manager. This allows us to layer our environments instead of destroying them. For example, if you look at our code snippet here on the left, when a player hits the escape button in the demo scene, the manager pushes the pause scene onto the top of the stack. Because the manager calls upon the update method on top of the scene, the physics and game logic completely freezes. However, the pause scene is designed to still call the previous scene's render method, which is how we keep the game visible in the background while the game is being paused. To keep our architecture clean, we rely heavily on abstraction. We use the scene control interface, which guarantees scenes can trigger state changes, like push, pop, or set, without ever needing to know how the manager operates underneath the hood. So, moving on to the next slide, let's look at how the scene acts as the game director, so to say. Every scene inherits from the abstract scene class, which enforces the polymorphic behavior. It guarantees that every scene has the standardized update, render, and dispose cycle. Our demo scene is a perfect example of composition and separation of concerns. It encapsulates its own specific physics world, camera, and even viewport. This means different scenes can have entirely different rules and zoom levels without interfering with each other. If you look at the demo scene update loop snippet here on the left, you'll see it doesn't actually calculate math or physics itself. It simply holds instances of the other managers. It tells the physics world to step, the movement manager to move entities, and the collision manager to resolve impacts. By delegating these tasks, the scene acts as a central hub, bringing all our abstract systems perfectly together into one cohesive game loop.
This is Yixuan with student ID 2502446. First we have is an entity manager. It manages a list of entities and utilizes polymorphism in rendering, meaning that the entity manager doesn't need to know if an object is a texture object or a geometric shape. It simply looks through the entity list and calls the draw method, allowing the subclass to handle its own unique visual representation on the screen. So this entity manager also implements the iMovable and iRenderable interfaces to bridge the gap between the managers. The iRenderable interface allows the scene manager to render and draw entities, while the iMovable interface allows the movement manager to update its position, hence moving them without either of the managers needing to access the private data of the entity. Moving on, we have is the entity class. So this class provides a common set of spatial data and rendering code so that the engine can treat all objects polymorphically. So this entity, to support the different entity roles for the movement manager to assess which entity can move, we have 2 primary extensions from the abstract entity. One is the movable entity for dynamic entity that have movement, either due to input-output from the user or AI default movement. The second abstract class we have is a non-movable entity for static environment pieces like boundaries for the collision system to use. Now, due to our 2 primary extensions from the abstract entity, movable and non-movable, here, our system currently supports varied implementation from texture, such as texture object, to geometric shape such as demo circle and demo triangle. Looking at one of the examples, demo circle, we use protected fields over here, such as set position, set width, set height, to ensure the external classes or the managers can interact with the entity safely without breaking into the internal state of the entity. So in this example, we use shape renderer to draw a circle based on its characteristics. Each entity will have its own draw method using polymorphism, specifically overriding, specializing in the sprite batch for text objects or shape renderer for vector graphics.
Hi, my name is Sanrong, 2303331, and I'll be going through our abstract engine's movement system. Let's walk through exactly what happens each frame. Firstly, demoscene.update runs, and it calls work.step to advance the physics simulation, then immediately calls movementManager.movement. Then Movement Manager loops through its entire list of movable entity objects and calls entity.move on each one. Next, each movable entity receives that call and immediately dedicates to whatever iMovement type strategy is assigned to. Movable entity itself contains no movement logic whatsoever. The assigned strategy, whether it's AI, physics, or keyboard control, executes and either directly modifies the entity's position or applies forces to its physics body. The key point here is that there is no movement logic living in Movement Manager or movable entity. It's entirely pushed down to the strategy. All four strategies implement the same iMovement type interface with the same single method, move. But what that method does is completely different in each case. For example, empty controllable movement reads WASD keyboard input every frame and directly adjusts the entity's X and Y position. It also supports right-clicking to teleport the entity to the mouse position. Empty physics movement is entirely passive. It reads the Box2D's body, position, and rotation each frame and copies those values into the entity. It also handles respawning if the entity falls out of the world. All four plug into any movable entity with zero changes to the entity or the manager. Empty AI movement requires no input at all. It tracks how far the entity has moved and flips its direction every 15 units, creating a simple left to right patrol. Finally, we have empty physics control. It reads the arrow keys and spacebar, but instead of setting position directly, it implies impulse forces to the Box2D physics body and lets the engine resolve the motion. Thank you.
I'm Jinhin 2500928, and I'll now be talking about the input and output architecture for our abstract engine. Our main goal was to safely manage all hardware devices outside the core game loop by creating a centralized hub. As you can see in the first code snippet, it stores all active devices in a hash map. This provides instant retrieval. The engine can simply look up the device via string keys like a keyboard or mouse, without passing heavy object references around. This manager also leverages polymorphism for the memory cleanup. In the dispose method shown at the bottom, it simply iterates through the generic device objects. At runtime, calling dispose dynamically executes the specific memory disposal for that exact device, whether it's clearing or shutting down a hardware listener without the manager needing to know the specific device type. Moving on to device abstraction and segregation, instead of letting the engine talk to the hardware directly, I created wrapper classes to decouple the complex libgdx hardware calls, keeping the engine completely agnostic. In the top snippet, you can see the input device class. This demonstrates composition or a HESA relationship. It bundles a mouse and a keyboard into a single cohesive input wrapper so the engine can query inputs from one unified place. Lastly, I applied the interface segregation principle to our audio system. Instead of a massive audio interface, I separated the audio contracts into iSound for overlapping sound effects and iMusic for streaming background loops. This ensures systems only implement the specific methods they actually need. That covers the I/O architecture, and I'll pass the time now to the next presenter.
Hello, my name is Kamlesh, and I'll be discussing mainly on the collision system. The detection stage happens inside begin contact from the Box2D contact listener. Instead of resolving behavior immediately, I first extract the entity objects from the physics bodies using user data. After validating them, I push both entities into a resolve queue. The important part here is that detection only records the interaction. It does not decide behavior or modify positions. This prevents issues that happen when physics objects are changed during callbacks and keeps detection separate from gameplay logic. During the update phase, the queued entities are processed in pairs. Each pair represents one collision detected earlier. The system calls on collision on both entities, which forwards the event without knowing what the objects actually do. This step acts as the dispatch stage of the pipeline. The collision listener remains generic and simply routes events to entities, keeping gameplay logic separate from detection. At the entity level, collisions are routed through a single entry point called onCollision. The entity itself does not contain behavior logic. Instead, it delegates to response strategy object. This follows the strategy pattern from object-oriented design, allowing different entities to attach different behaviors while keeping the collision pipeline unchanged. This abstraction keeps the system loosely coupled and flexible. Now lastly, the response layer defines actual gameplay behavior. For example, the droplet response checks the ID of the entity it collided with and performs actions such as repositioning or playing a sound. Because behavior is isolated in response classes, new interactions can be added without modifying the collision system itself. Mouse click detection is also placed under the collision system because it follows the same mechanism. Instead of detecting physics contact, it queries the Box2D world at mouse position and triggers on collision on the selected entity. From the entity's perspective, a mouse click behaves like a special collision event, which allows input interactions and physics interactions to share the same dispatch pipeline.
That brings us to the end of our presentation. Thank you for your kind attention.